All right, welcome everybody to our September OpenXLA community meeting. This week it was delayed by a few days. Last week the team was at the PyTorch conference. So what I wanted to do, this meeting is only going to be 30 minutes, just give you kind of a very high level about OpenXLA's presence at the PyTorch conference. We'll do a deeper dive in October, but just wanted to kind of give folks like a sense for what all happened. Just let you know that there's an LLVM Shardy talk happening October 22nd to the 24th, and then we'll dive deep into HLO composites and componentization, and we've got the team here to present that as well. So just really quickly, I know we're going to do a deeper dive. We had an OpenXLA booth. I mean, it was widely successful. It was really nice to see the excitement and all the great questions that we got. Google also sponsored the lunch reception as well. We had Jacques who presented during one of the lightning talks. He was also on the panel. And then Shaheen talked about PyTorch and OpenXLA. And in the evening, we hosted a OpenXLA reception that was open to the entire community. And that was a completely full house. I mean, we were just sold out and we had more folks that wanted to come, but we just didn't have the space. But hopefully next year we'll do something even bigger. And then to just remind everybody, LLVM is happening October 22nd through the 24th in Santa Clara. Google DeepMind and CoreML, they'll be presenting Shardy. I know we had introduced that earlier in the year during one of the community meetings and also a dev lab. So please go check out those videos if you wanted more background. But the team will be flying out from London for that meeting. So hopefully we'll see many of you there as well. And then, Kevin, let me turn it over to you for the RFC.
Cool. Yes, thank you. I'm going to try to get the author of this RFC to present at the next community meeting, but that will be after the RFC period has concluded. So I just wanted to signal boost this in the meantime. But this was an RFC that came from an NVIDIA dev about having explicit async ops in stable HLO so that you can be explicit about scheduling as opposed to relying on XLA to generate optimized schedules, which has been a difficult and challenging problem. So yeah, there's the link there. Please take a look at it. Thanks.
Perfect. Thank you, Kevin. And then let's turn it over to Gunyon to talk about HLO composites.
Yeah. Hello, everyone. I'm Gunyon Park, and thank you all for attending today's meeting. I've been working on HLO composites a couple of weeks ago, and I'm here to tell you all about it. Now, this presentation kind of assumes some background knowledge on stable HLO extensibility RFC that was merged earlier this year, which is very much related to this and obviously inspired by the stable HLO composite op. So I hope you'll find it useful and use it. So let's get right into it. Yeah, so quick agenda. I'll first go over what HLO composite is, why it's there, current use cases, and some key takeaways from this presentation, and what's to come next. As you might already know, composites can be used to encapsulate an operation made up of other primitive ops. And composite op was added to stable HLO earlier this year, and users are using the op as a super convenient way to capture abstraction on stable HLO. Some folks are directly emitting HLO from frameworks via the PyTorch XLA bridge, and it will be useful to preserve this abstraction in HLO. So I brought the same thing here. HLO composite is implemented using a call op with metadata attached to it. I went with this approach instead of creating a dedicated composite op because unlike HLO, stable HLO doesn't have a function call op. So I added a isComposite flag here to differentiate regular calls from composite calls. And with a dedicated composite op in stable HLO, you can store metadata for your op as MLIR attributes, but here in HLO, the attributes are stored inside the front-end attributes dictionary. All composite attributes are prefixed with the composite namespace followed by the attribute name and value, which is the same exact convention that we use in stable HLO. So currently the composite attributes are stored as MLIR dictionary strings for easy lowering from stable HLO, and this was inspired by the custom calls typed FFI. Before we had composites, custom calls were the kind of the norm, and backend config contained escape strings here on the top. So reading the attributes were very difficult. So later, this API version typed FFI was introduced to tackle this. And you can use this by specifying the custom calls version attribute to 4. But I think there's still room to improve on UX with custom calls, especially with a lot of backend config attributes to be used as a replacement for the composite op, which has relatively, I think, few attributes. So I enhanced this call op so it can be used for composites, and front-end attributes can now fully support parsing MLR dictionary strings, and this is, I think, much easier to read than the old version. After stable HLO composite was added, it is now used by ODML for quant and dequant operations internally, and we had positive feedback on its use case. And they share that composites make pattern matching easier using a dedicated composite op versus the custom call method. And current known use cases from our partners is Intel will be using HLO composites for their quantization efforts. And there were also a few who were interested in using HLO composites once it's available to use for their own accelerators to pattern match like attention blocks and having this abstraction preserved in HLO. If you go back to the previous slide. Yeah. Let's say like I have a high-level op like softmax or tension here instead of, I guess, foobar, and I want to preserve this abstraction. Then I can wrap it in a composite. And could you go back one more slide? Yeah, perfect. So I can wrap it in a composite and define the decomposition separately as another func call op here. Instead of add, here it will be attention or softmax. And this way, your hardware can kind of fuse this with other ops without kind of having to worry about pattern matching the decomposition or a custom call. And I imagine there will be more creative uses of composites from you all. And so I'm kind of looking forward to your contributions if you have any ideas. Yep. So I hope this was a good overview of what HLO composites are and how to use them. But if anything, there's two, I guess, takeaways is to, if you're using a custom hardware specific and you're lowering an op, please use composites. Stable HLO composites can now lower fully to HLO without, I guess, kind of losing this abstraction you want in your accelerator. So, and if you don't need it, the HLO inliner will inline them by default. And unlike stable HLO composite op, HLO composites are implemented as a call op with the is composite flag set to true. So one user journey I highlighted was to wrap your op in a composite to preserve this abstraction in HLO without having to pattern match. And the path to wrap your op in this composite is currently under works, and I would love to know if you plan to use it. And like I said before, the composite call is inline by default. And the next step is to add a flag in the inliner to take additional parameters to disable inlining composites for abstractions that you want to keep. And again, this requires community interest. So if you have potential use cases for this, please reach out to OpenXLA Discuss, or you can also directly reach out to me.
Great.
And yeah, that's it for my presentation.
Any questions? Thank you, Gunyan. All right, so let's move on to Sandeep. think you're on mute.
Thanks, Aditya.
No problem.
Hello, everyone. I am Sandeep Dasgupta, and I'm here today to discuss HLO componentization. HLO is a crucial part of XLA, the framework that we use for machine learning model compilation. As XLA has evolved, the HLO codebase has become quite complex, making it difficult to navigate and contribute to. This presentation outlines a proposal to address these challenges by restructuring HLO into a more modular and well-organized component. So here we are, what we will be covering today. First, I will detail the specific problem we are facing with the current HLO structure. Then I will present a proposal for reorganizing HLO into a self-contained component. We'll define what a component is. We'll delve into the design philosophy guiding this componentization effort. Finally, we lay out the implementation roadmap for bringing this new structure to life. Next slide, please.
Mhm.
The current XLA structure has grown organically over time, leading to a complex and challenging organization of files. For example, if you see the XLA service, XLA client folders, they contain hundreds of files related to HLO, but they lack clear organization. This makes it difficult for developers to find what they need, understand the relationship between different parts of HLO, and contribute effectively. Additionally, the lack of clear boundaries between components hinders code quality improvements and refactoring efforts. Also, one thing to note here is that the test coverage that we publish and that can be obtained today, they mainly rely on integration testing with no understanding of what the unit level coverage is. So that is something that can be improved with this componentation effort as well. Next slide. To address these issues, we propose to create a self-contained HLO package within XLA HLO directory. This component can be thought of as a basal package, which will house all aspects of HLO, including C++ and protobuf definitions of the IR, operation builders, parsing tools, Python bindings, tests, documentations, and developer tools. The idea here is that we will create a clear and well-defined boundary for HLO, making it easier to understand, work with, and contribute to. This approach aligns with the successful componentizations of stable HLO and MLIR, which can be thought of as a well-defined components, where dedicated directories encapsulate all their functionalities. For example, the IR, dialect, passes, they are all encapsulated, ensuring a well-organized and easily navigable code base. Next slide. So what are the benefits? So they have some key benefits. First, we'll improve the maintainability by making the code base more organized and easier to understand. Second, it will foster collaboration by providing a clear structure of contributions. Third, it will simplify and encourage external contributions by making it easier for new developers to get involved. Fourth, it will ensure code-based robustness by enabling component-level coverage statistics, and we will show some examples of that, making it easier to identify and address the gaps in testing. Next slide, please. So the design of HLO component is guided by some key design principles. The traditional XLA architecture has a clear client-server model where the client builds the HLO graph and sends it to the server for completion and execution. However, this approach, particularly for remote execution, hasn't yielded the expected performance benefits. Contrastingly, the PGRT client eliminates the need for a separate server and it opts for a direct communication with the local device driver. With all this learning, we aim to design HLO as a unified component, avoiding the client-server distinction to potentially streamline the compilation and execution process. Second, we will enforce separation of concern among subcomponents to ensure clear boundaries and responsibilities. In the subsequent slides, we will examine the various subcomponents and their corresponding responsibilities. Third, we will provide clear and comprehensive documentation to guide developers. And finally, we'll improve testing and coverage to maintain high quality. Next slide, please. So here's a visual representation of the proposed component structure that we have been working on. The XLA HLO directory will contain subdirectories for various aspects of HLO, such as IR creation, parsing, building of high-level operations, pass infrastructure, transformation passes, tools, interpreter, Python integrations, and documentation. We believe that this structure will ensure each subcomponent has a clear and well-defined responsibility. Next slide, please. The implementation will consist of two main phases. The first one is what we are working on, which is called the directory level refactoring, which moves relevant files to the XLA HLO directory. The phase is already underway with subcomponents like XLA HLO pass and XLA HLO translate already in place. Here and also we will be building aliases to avoid unexpected surprises during development workflow. So the picture, you can see the latest unit test coverage report for recently developed subcomponents. This detailed coverage report, made possible by componentization, helps us pinpoint areas for improvement and guarantee the reliability of each HLO subcomponent. Now, the phase 2 will involve file level refactoring, splitting existing files to relocate logic closer to its most relevant subcomponent. As an example, the existing HLO verifier .cc and .h, the code there encapsulates both the fundamental verification infrastructure as well as operation specific checks. If we following the MLR's componentation approach, we can reorganize this code to separate the generic verification infrastructure from the operation specific checks. Next slide. Next steps, we will actively working on creating the remaining subcomponents and refining the structure. We'll also focus on improving test coverage based on the current coverage report. File level refactoring is an ongoing effort to enhance modularity, readability, and maintainability. At OpenXLA Discuss, I cordially invite everyone to share their valuable feedback on this project. And with that, your time and contributions are greatly appreciated. Thank you. Any questions you have?
Perfect. I guess there's no questions. All right. And
Actually, I had a question
Sure.
regarding the developer community. You said that there are going to be a detailed instruction and cookbook. How we can, like, how soon we can get those things?
So some of this, I think you specifically meant some kind of cheat sheet or kind of documentation which will help navigate the code base and also how to use it. So some of these documentations are already under development. So as we create a component or a subcomponent, we already started populating documentation regarding that. For example, the ones which are already created, for example, XLA HLO pass, you can see a documentation, README file, which will not only help to navigate the code base, but also help how to use the pass infrastructure. So some of these efforts are already ongoing. And one thing we can do is that as and when we are having a better structure, we can inform the community using the XLA Discuss, so that we all will be informed about the progress that we are making. What do you think about that?
No, I think that's great. Thank you. I'll take a look. Thank you.
any other questions? Kevin.
Yeah, not a question. I guess I just wanted to reemphasize for these migrations, as Cindy mentioned, we're doing it in as minimally invasive and non-breaking of a way as possible and giving time for migration. We will have one OpenXLA Discuss thread where we post all of the migrations as it comes time to do them. So I guess once that thread exists, we'll signal boost it and just keep tracking that one.
Jaya?
Yeah, so question about the separation between different pipelines like CPU, GPU, and so on. Would that how do you plan to organize your folder structure?
Yeah, that's a very good question. So right now the component that we are focusing on is mostly hardware independent. For example, the HLO component, you will see that even the passes that we are trying to put in separate subcomponents of HLO, they are going to be hardware independent. For the hardware dependent components, as you said, like CPU, GPUs, there will be separate effort, and I think they will be published when the time comes. But right now, the effort is only for the HLO hardware independent components. But I believe that for those components as well, hardware dependent ones, there'll be separate components, and a lot of effort will be put in reorganizing them and publishing the progress on that.
Got it. Thanks.
Pushkar?
Hi, I had a question about the previous presentation, if that's okay.
Kunyan's here.
Yeah, so perhaps I missed this part, but are the Python bindings for the builder APIs for composite op also implemented? Because we would like to use, directly lower from the framework.
Kevin, do you know the answer to this?
Yeah, all of the, I guess, which framework in particular?
JAX or
Yeah,
even
okay. So if JAX is going through the MIR Python APIs, then yes, all of it is already there. I don't know if this has any formal built-in JAX support yet, but it is certainly possible via custom primitives is how I believe ODML team has leveraged this from JAX. But yeah, define a custom primitive, define its MLIR lowering using using the MLIR Python APIs, and composite op is fully accessible there.
Cool. Thanks.
We've got 6 more minutes. Any more questions? All right. Okay. Well, thanks so much, Kunyan and Sandeep, for your presentations. Next month, we'll focus on the PyTorch conference and some of the talks that were given there. And then if there's any other topics that folks want to cover, please do reach out so that I can get you added to the agenda. Thank you again, everybody.
Thank you. Thank you, everybody.